Greetings everyone and Happy New Year! I hope you all had a wonderful holiday season and that you're excited to get back into another year. I'm sure I'm not the only one who missed our December MathFix, so without further ado, let's get started.
Today's MathFix is brought to you by G.GMD.3, which asks students to use volume formulas for cylinders, pyramids, cones, and spheres to solve problems. Let's take a look at our problem today. Students are asked to determine the dimensions of the smallest dunk tank they should rent to be cost-effective, but also fully dunk any teacher that agrees to participate in their school carnival. Where might students start with this? Let's jump in. Students might want to start by first estimating the dimensions and volume of the teachers they might be dunking. It might be wise to start with thinking about the largest teacher to make sure all teachers fit. For example, to err on the large side, they might assume a height of about 7 feet and a width of about 2 feet. From here, students have a lot of freedom and flexibility in how they imagine the dunk tank. Do they want a cube, a rectangular prism, a cylinder, some other shape of their own invention? Students might have a linear thought progression on this problem, and that's okay. For example, they might start by choosing a rectangular prism for a tank. To be super safe, they might assume a height of, say, 7 feet and a square base with length and width of 4 feet. This would almost certainly cover any teacher, even standing straight up. Using the formula for the volume of a prism then, they would get a volume of 112 cubic feet. While students don't know what the price per cubic foot is, they can assume that they can get a cheaper tank by minimizing the volume. Let's explore some ways students might do this. Keeping with the rectangular tank, students might assume that they can cut the height in half, noting that teachers don't need to be standing straight up and down when dunked. They might end up in a seated or even bent over position. What does cutting the height in half do to the volume? It cuts the volume in half. What if they wanted to keep the height but decided that a 4-foot square base was too big, and they cut each of those sides in half? What would that do to the volume? Well, since in the volume formula the base is squared, it turns out that the volume is actually cut into quarters. That really helps with the cost of the dunk tank. But is this tank big enough? Students might want at this point to shift away from exploring rectangular tanks and instead try cylinders. To be safe, let's say they again assume a height of, say, 7 feet and a diameter of 4 feet, so a radius of 2 feet. This would be comparable to the first rectangular tank, but using the formula for the volume of a cylinder, they would get an approximate volume of 88 cubic feet, so it appears so far that perhaps a cylindrical tank might be more cost-effective. Continuing with our logic from before then, and keeping with the cylindrical tank, students might again assume that they can cut the height in half. With this shaped tank, does it again cut the volume in half? You bet! What if they decided, similar to with the rectangular tank, that a 2-foot radius was too much and they cut that in half? What would that do to the volume? Well, since in the volume formula radius is squared, it turns out that, similarly, the volume is actually cut into quarters. That really helps with the cost of the dunk tank and is our smallest volume yet. Students might want to keep exploring changing the parameters. For example, what if they cut the height down and the radius? This really decreases the volume, but is it realistic? Will it allow all teachers to fully submerge? These are the kinds of questions students will need to think about as they make decisions about their ideal dunk tank dimensions. They may even want to explore other shapes.
And there you have it, folks, the January MathFix. As you know, we love hearing about what you're up to in your classrooms all around the globe, so don't hesitate to share with us your take on this month's problem. Until February,